Thanks very much, Lev and Stanislav, for the invitation. It's a real honor to speak to the seminar. So I'm going to talk about a recent paper called Logics of Imprecise Comparative Probability, which is joint work with Yifeng Ding, who's in the group in logic at Berkeley, and then Thomas Eichardt from Stanford, who is here with us today. And this is forthcoming in the International Journal of Approximate Reasoning. You can already find it online. And what I'm going to try to do today is give a big picture storyline that goes as follows. There's a lot of details in the paper, which you can find there, but I want to give the following main topics today. One is, what is comparative probability? Some of you may already be familiar with that. What is imprecise probability? And how do we connect these two things together? And so I'm going to first talk about representation theorems that talk about when a comparative probability relation can be represented by a probability measure or by a set of probability measures. And then I'm going to talk about logic. So I'm going to introduce formal languages and use the representation theorems to prove completeness theorems. I'm actually not going to do the proofs today, but I'm going to tell you what they say. Then I'm going to talk about a number of language extensions. So the basic language is just going to reason about whether one formula is at least as likely as another formula or more likely. And then we're going to consider three language extensions. One is going to add an epistemic possibility modal, a diamond. Another is going to talk about the updating of probability in response to new information. So for those familiar with dynamic epistemic logic, this is going to be a case of dynamic epistemic logic. And finally, I'm going to talk about becoming aware of a new proposition or a new concept, and how we can model that also in this dynamic style. And then afterward, I'm going to talk about a few open problems because I want to use this talk as a kind of advertisement for logicians to get interested in logics of comparative probability. So that's the plan. And please feel free at any time to interrupt with clarification questions or anything like that. Okay, so let me start with comparative probability. So the idea is that, well, according to one school of thought in the foundations of probability, we should take as our starting point a binary relation between propositions or events, where we read this binary relation as A is at least as likely as B. Okay, and that's the fundamental primitive. We could also talk about A is strictly more likely than B. We'll talk about that shortly. And once we have this idea of taking this as our starting point, we then, of course, ask the questions, what axioms should this binary relation obey? Some obvious ones, reflexivity, transitivity, but there are also some interesting axioms. For example, you could think about this principle, which is sometimes called qualitative additivity, which says that if some set C is disjoint from both A and B, then A is at least as likely as B if and only if A union C is at least as likely as B union C. And you can immediately see that if you're thinking of this inequality in terms of a finitely additive probability measure, assigning a measure to A at least as great as it assigns to B, then of course this equivalence will hold, right? Because the probability of A union C, given that they're disjoint, will just be the sum of the probabilities of A and C. And similarly, on the right-hand side, you'll just have a sum, and so this equivalence holds. So that's an example of a kind of axiom that you might want to endorse. You might want to endorse it for reasons independently of thinking about numerical probability. You might give arguments directly for a qualitative axiom. Okay. But we can also ask, what's the relationship between the qualitative relation and numerical measures of various kinds? So in general, we want to ask, when is this binary relation representable by finitely additive probability measures? You could ask about countably additive probability measures and other kinds of measures, possibility measures, plausibility measures, all kinds of things. So that's comparative probability in one slide. And now let me give you imprecise probability in one slide. So the idea here, the imprecise probability school critiques the assumption of the standard probability calculus that every proposition is assigned a precise real number probability value. And you can critique this both descriptively. You can argue that when we are describing how agents behave, it doesn't make sense to attribute to them a precise subjective probability in a proposition. There are various behavioral economics experiments, and we'll talk about one of them, which might call into question the assignment of a precise probability value to a position for an agent. You could also criticize the precise assumption from a more normative point of view, to say that in certain situations where you lack evidence, it would be inappropriate to go beyond the evidence and assign a precise probability value. Okay. So there are both descriptive and normative critiques of the idea that to every proposition you assign a precise probability value. So the imprecise probability school says, let us represent an agent's state of uncertainty with a set of probability measures that may not be a singleton set. So we may ascribe to the agent, we say that their subjective state is best represented by a set of probabilities. And then what is an agent's attitude toward a single proposition A? We can think of that in terms of a set of possible probabilities given by applying every measure in the set to this proposition A. Or you can think in terms of the interval of probabilities. You can look at the inf and the sup of these possible probabilities. So this is related to what's called interval valued probability, where you think that instead of having a precise real number for the proposition A, I have some interval that represents my attitude toward the proposition. So how do we put these two things together, comparative probability and imprecise probability? Well, there's a straightforward idea for doing that, which is to define this binary relation as a kind of unanimity relation. You think of all the measures in the set as voters. You say that A is at least as likely as B if and only if, according to all measures in the set, the measure of A is at least as great as the measure of B. Okay? So this is not the only binary relation that we will consider defining from a set of probability measures, but we'll start with this. In this case, we say that this binary relation is represented by the set of probability measures as the weak relation. Okay? It's a weak relation, it's reflexive. It means at least as likely as. And later I'll talk about a primitive strict relation. Let's start with the weak relation. Now again, thinking about the connection between comparative probability and numerical probability, we can ask what axioms on an arbitrary binary relation on, let's say, a power set of a finite set, that's what we'll start with, are necessary and sufficient for the existence of some set P of measures that represents the initial binary relation as the weak relation. Okay, so that's the representation question that we want to address.
And so, we don't have any kind of conditions on this set of measures P.
We could ask additional conditions, but in the first instance,
so far we have no conditions, and this situation also makes sense without additional assumptions on P.
That's right. In fact, that's what the main theorems that I'm going to present today. There's of course a huge literature on this, but the main theorems that I'm going to present today just ask for the existence of any set of measures that represents the relation. That's a very good point. Okay, so I want to motivate a bit imprecise probability in case you're not familiar with the literature on this. Why do we care about this set of measures representation? So I think the following example is helpful. This is from, I would say, behavioral economics, the famous Ellsberg Paradox by Daniel Ellsberg. And it has spawned a literature in economics about so-called ambiguity aversion. So here's the example. You have an urn of 100 marbles, and 30 of the marbles are known to be red. The other 70 are blue or yellow in some unknown proportion. Okay, that's the setup. Now let me tell you, I think, some generalizations about humans in response to this example. First is that often people prefer a bet that yields $1 if they draw a red marble. Remember, it's known that 30 of the marbles are red. They prefer a bet that yields $1 if they draw a red marble over a bet that yields $1 if they draw a blue marble. Remember, they don't know how many blue marbles there are. They just know they're blue and yellow in some unknown proportion. So I'm curious, do other people, does that sound, I should have done an experiment and had you make a judgment before I told you what other people do. So now it's a biased sample. But is that an intuitive preference? People find that intuitive? I've noticed that sometimes if you tell a scientist this, they don't like this preference that people have.
Well, seeing what is coming, it's not so intuitive.
Seeing what is coming,
anyway.
Yeah. So Val thinks ahead several steps.
Yes.
Yeah, good. But anyway, a lot of people have this preference. And in light of that, it suggests that they do not judge that drawing a blue marble is more likely than drawing a red marble. Because if they judge that drawing a blue marble is more likely than red marble, then they should prefer the bet that gives $1 if they draw a blue marble over the one that gives them $1 if they draw a red marble. Okay. But we can't really model this with a single probability representation, because the natural choice, maybe the only choice that you could defend, given what I've said about the example, is to take a measure where the probability of drawing a red marble is 0.3, and the probability of drawing a blue or yellow is evenly divided between the 0.7 that you have left, so 0.35 for each. So then that gives you that B is strictly more likely than R. Drawing a blue marble is strictly more likely than drawing a red marble. So you can't really represent people not making the judgment that blue is more likely than red with a single probability measure, but you can with an imprecise probability representation. So here's just one idea for how to model this with a set of probability measures. You look at the set of all measures mu sub n, such that n is a natural number from either 0 up to 70. And they all assign the probability of drawing a red marble to be 0.3. But mu sub n says that there are n blue marbles. So the probability of drawing a blue marble is n over 100. And the probability of drawing a yellow marble is 70 minus n over 100. Okay. So intuitively, you know what the probability of red is, but you don't know what the probability of blue and yellow are. So you have all the different measures that are compatible with your evidence. Okay.
Mm-hmm.
Good. Now, if you apply the definition of the comparative relation, at least as likely as, to this set of measures, remember it's a unanimity relation, so it requires all measures in the set to agree that, you know, one proposition is at least as likely as another, then we'll see that red and blue, you do not make a comparative judgment between them. You don't affirmatively judge that red is at least as likely as blue. You don't affirmatively judge that blue is at least as likely as red. Right? Because you have some measures that give blue a higher probability than red, some measures that give blue a lower probability than red. You don't make an affirmative judgment. Now, if you plug in a decision rule, this is a standard decision rule to consider. You pick the bet, you look at, for every measure in your set, what is the expected utility of a bet? And you record what is the worst case expected utility that I could get for a bet, looking at all my different measures. And that's the value that you use for a bet to compare it to other bets. So if you pick the bet whose worst case expected utility according to all the measures is highest, then you're going to prefer the bet on red, because you know there are 30 red marbles. Whereas, you know, you could be very unlucky and there could be very few blue marbles, giving you a very low expected utility according to one of the measures in your set. So this is one attempt that economists have come up with to explain the preferences that people exhibit in the Ellsberg situation. Okay, any questions about this example and how it at least motivates us to look at imprecise probability as an interesting representation?
So the point is that you want to make is that this comparative probability somehow more faithfully represents the situation that you described in this example, for example, right? So, okay.
And especially the incomparability between blue and red, which is something that we can't have with a single precise probability measure.
Okay. Okay.
So that will be important to the question of what is the logic of comparative probability. According to imprecise probability, we see already that it will not have an axiom of comparability. Right? We can refute that in this example.
Okay.
Okay.
Good.
So I'm not going to give a very dogmatic argument for imprecise probability. I'm approaching this like a logician, looking at the different systems, but I want to at least motivate for you why people are interested in this. Okay, so let's talk about now representation of a binary relation, let's say on the power set of a finite set, by first a single probability measure, that'll give you the background context, and then by a set of measures. So here's a very famous result by Kraft, Pratt, and Seidenberg, which was also put in an especially nice form by Dana Scott. So we have a non-empty set W of possible worlds, and we have this binary relation on the power set. And I want to ask, when is this thing represented by a probability measure? And that's just a special case of what I already defined. I defined it for a set of measures, but we can consider a single measure. So this means that A is at least as likely as B according to the binary relation, if and only if the measure of A is at least as great as the measure of B according to the probability measure. So what are the necessary and sufficient conditions for this? First, some kind of obvious ones, that it shouldn't be that the empty set is at least as likely as the whole set. And it should be that every singleton set is at least as likely as the empty set. So some kind of obvious ones that we have to throw in. Then the axiom of comparability. Very important to distinguish between precise and imprecise probability. So any two propositions are comparable in this relation. And then the real key to the whole game is what's called a finite cancellation condition. Okay, so finite cancellation says, well, first of all, some notation. So I'm going to use this bold 1 sub x to be the characteristic function of x. And now let us consider two finite sequences of propositions, the AIs and the BIs. What this equation means when we're doing these additions in this vector space is that every world in W belongs to exactly as many A's as it does B's. So if you look at W1, and if it belongs to 7 of the A's, exactly 7 of the A's, then it must belong to exactly 7 of the B's. Okay. So we'll say that these two sequences are balanced when every world belongs to exactly as many of the A's as it does to the B's. Suppose that's the case, and suppose that for all I strictly less than n, AI is at least as likely as BI. Then what this axiom says is in order to keep the balance at the level of probability measure, it must be that Bn is at least as likely as An. Because if An were strictly more likely than Bn, well, you can see that's incompatible with this balancing. Every world belonging to exactly the same number of A's as it does to B's. Okay. So it's not hard to convince yourself of the soundness of this axiom. What is harder to see at first is how to use this axiom in derivations. Okay. And I'll mention later that there's another way to think about the axiomatization that's interesting from a proof theoretic point of view, using a Gabay style rule. I'll just mention that in passing. We can write this in a formal language, which I'll mention a few slides from now. Okay, you can also give an argument. Now, stepping aside and being more philosophical, you can also give an argument, and Thomas has written a whole paper about this, that a rational agent, their comparative probability relation ought to satisfy this finite cancellation condition. And if they didn't satisfy it, then they can do some pragmatically irrational things. They could get into trouble when accepting bets, for example. Okay, I'm not going to give that story here today. So that's just the background on precise probability. And now I want to consider an analog of this for imprecise probability. So we'll see how the axioms change. By the way, I should say, this is a good exercise, although maybe it's a little annoying, but you can use this to derive, for example, that qualitative additivity axiom that I put on the second slide. Okay, and you derive other things from these axioms like transitivity, that's all. Okay, so the next part in our story is the imprecise probability representation. So again, we have a finite set and a binary relation on the power set. And what we're going to ask now is, when is the binary relation represented by a set of probability measures as the weak relation? Okay. Now, we should expect that those same conditions we had before, the first ones, should hold. But we drop from the axiomatization the the comparability principle, that any two propositions are comparable in likelihood. And you might think, as we initially did some years ago for a minute before finding this paper, that that's all you do. You might think, look, when going to the imprecise probability setting, why don't you just drop this and keep everything else the same? And interestingly, that doesn't do it. You also need to strengthen the finite cancellation condition to what's called generalized finite cancellation. And the only difference there is that when you have your two sequences of events, you then basically form two new sequences where you're allowed to make k copies of the last proposition, an. So that gives you kind of an augmented sequence. So a1 through an, and then k copies of an, and then b1 through bn, and then k copies of bn. And now we say that if those augmented sequences are balanced, so that's all this is saying. It's saying that every world belongs to exactly as the same number of augmented A's as it does augmented B's. Then we have the same conclusion that we had before, that if each A less than n, for I less than n, is at least as likely as Bi, then to maintain the balance, Bn must be at least as likely as A. Now, this is also puzzling. Like, what is this copying of the last element doing? How does this give you more strength than finite cancellation? And for that, we have a paper about that, actually. So in the previous literature, this was used to prove the representation theorem, but it wasn't actually shown that this wasn't just derivable from the conditions of the previous slide minus comparability. So you can actually come up with relations that satisfy these axioms here in part one, and satisfy the finite cancellation condition, where you're not allowed to go to this augmented sequence with k copies of the last proposition. So they satisfy finite cancellation, but do not satisfy generalized finite cancellation. Those are already fairly complicated examples, which you rule out with generalized finite cancellation, but you don't rule out with finite cancellation.
So in the presence of a comparability condition, you will get
yes.
You can derive it, but not
exactly.
without it. Mm-hmm.
Exactly.
Okay. Mm-hmm.
That took some thinking to try to cook up an example.
Mm-hmm.
A little background on this. We got interested in this because there's a literature on reasoning about relative likelihood in natural language. So people often say things like, "Oh, that's more likely than that," right? Mm-hmm. And we were interested in what logical principles speakers of natural language might actually accept, what inference principles they might accept. And, you know, like that qualitative additivity axiom that I put on the second slide, you might think that ordinary speakers can make inferences using that principle. And we started to wonder whether people can make inferences according to, you know, like these finite cancellation conditions and so on. And how about this generalized finite cancellation condition? So it's interesting to look at the complexity of the examples that you need in order to distinguish these different logics. So already this kind of example that we give that satisfies the finite cancellation but not GFC, it's a very mathematical example that you couldn't necessarily put in the context of some natural language story that what ordinary speakers would understand.
May I also ask if in this, both in either of finite cancellation or this generalized finite cancellation, one can restrict the number n of summands here in some sense? Do you know whether it's possible?
Yeah, that's a great question. And the answer is no, I think. So I think Dana Scott and Pat Suppies, I think that's a reference. Thomas could correct me if I'm wrong about that. I think that Scott and Suppies proved that you cannot. So they looked at this hierarchy where, and in fact, in one of our early papers, we talked a little bit about this, how you could cut it off and only have sequences of length 3, and then look at what's provable in that logic and so on. I think in that logic, you can prove qualitative additivity. I may get the number a little bit wrong, but I think it's 3. Okay. Good. Now, one interesting thing about imprecise probability is that there are actually 2 ways to think about the relation of more likely than. One, obviously, is you can just look at the strict part of the weak relation. That's what we're doing here with this notation, crossing out the sim under there. Okay. But there's another idea, which is to do a unanimous strict preference. So here we say that A is strictly more likely than B in this primitive sense, just in case all measures in your set agree that the measure of A is strictly more likely than the measure of B. Okay. So we want to ask what happens when you also have this primitive strict relation. And just to give a very simple example, note first terminology. When we have this relation in the second line, we will say that this strict relation is represented by P as the strict relation. And as a very simple example of how these 2 things come apart here, let us suppose we have 2 probability measures. And according to probability measure 1, A and B are equally likely. And according to probability measure 2, the measure of A is greater than the measure of B. Well then, if we think about these strict relations, we're going to see that in one sense, A is strictly more likely than B, in the sense that every measure gives at least as great measure to A as to B, and not vice versa. Okay, so we do have this, but of course we don't have this. Okay, we don't have that A is strictly more likely than B in this strict dominance sense. We could call this the strict dominance sense of more likely than. And it's an interesting question, actually, when modeling agents, which relation better captures their talk of, or their judgments of, that's more likely than that. Okay. Now, the first question we want to ask about these things are they interdefinable? And the answer is no. So in the paper, we give little examples, very simple, of sets, P and P prime of measures, whose weak relations are the same, but whose strict dominance relations are different. And vice versa. Sets of probability measures whose strict dominance relations are the same, but whose weak relations are different. Okay, so this is not interdefinable. So we then can ask the question, what about representing pairs of a primitive weak relation and a primitive strict relation? Okay, so yeah, we say a pair is represented by a set of measures if the first coordinate of the pair is represented as the weak relation of the set of measures, and the second relation in the pair is represented as the strict relation. So what is the representation in this case? Well, first we want this strict relation to be irreflexive and a subrelation of the weak relation. Those are obvious constraints. Next, we want that the whole set is strictly more likely than the empty set, and that each singleton is at least as likely as the empty set. Of course, we're not going to have the comparability axiom, that every two propositions are comparable. We will have the generalized finite cancellation condition, of course, for the weak relation, but we need to add another axiom called the strict generalized finite cancellation condition, which is very similar in that it says that if you have two sequences of propositions, and again, you're allowed to make copies of the last proposition to go to the augmented sequences, and if every world in your set belongs to the same number of augmented A's as augmented B's, if that holds, and all of the AIs for I less than n are at least as likely as BI, and there's some I less than n such that AI is strictly more likely than BI, then in order to maintain the balance, the last B must be strictly more likely than the last A. So it's of a very similar flavor, of course, to the previous cancellation axioms. And this is all you need now. And this is necessary and sufficient for the existence of a set of measures that represents the pair. Okay. All right, how am I doing on time? Okay. I now want to turn to logic. What we do is we take these representation theorems and parlay them into completeness theorems, right? But first, let's fix the formal language. So we have the language of propositional logic plus our two binary sentential connectives for the weak and strong relations. Okay. The semantics is given just as you would expect. So here M is a model consisting of a set of worlds and a propositional valuation. And we also evaluate formula with respect to a set of probability measures and a world. And the reason, just thinking ahead of why I've pulled out the set of probability measures notationally, is because when we do dynamics, we're going to want to modify that set of probability measures to interpret the dynamic operators of the language. Okay, so these clauses match exactly the notions of the unanimity relations that we had before. You know, phi is at least as likely as psi, just in case, according to every measure in the set, the measure of the truth set of phi, this is just the set of worlds where phi is true according to propositional model M and set of probability measures P. Right, so I'll be using this notation from now on. Just in case the measure of that truth set is at least as great as the measure of the truth set of psi.
So could you explain so exactly the meaning of this phi in square brackets with P? So is it the minimum or so how does it?
Yeah, so this is the set of worlds in W. Sorry, I got to write in my P. It's a set of worlds in W such that M E W satisfies phi.
Okay. So in a sense, nested probabilities are allowed, right?
Yes, that's a very important point. Yeah, nested probabilities are allowed. Yeah, that's actually an interesting point you make. For simplicity, in this talk and in this paper, we just have a global set of measures. In other work, we also consider world indexed measures. So every possible world W could have its own family of probability measures. So P sub W. And of course, you'd want to do that if you want to think about, you don't want certain iteration principles to hold. If you want to have agents who are uncertain about their own uncertainty, then you would want to consider world indexed families of measures. But we're not doing that here for simplicity.
Okay, so am I reading it right that so here the right hand side does not depend on W essentially, only the left hand side. So
exactly.
In a sense, this comparison proposition is either everywhere true or everywhere false.
Exactly. That's right. That's a very good point. So that's precisely this global point.
Mm-hmm.
The truth value of a comparison formula will not be world relative. It's going to be true everywhere or true nowhere. But of course, the purely propositional Boolean formulas, they are world relative, and that's why we can compare their measures. Right? Mm-hmm. But it's a straightforward extension to index these sets P by worlds, and then W would play a role on the right hand side, because what we would have up here is M, and then we would be looking at P sub W, right? And the set of measures would vary for different worlds. So I didn't say what M was, but M is just a pair of a non-empty set and then a propositional valuation for the proposition left. Okay, any other questions about this?
Yes, I have another question. So mu is just a countably additive measure on some sigma algebra of subsets, right? I mean, because some of these sets will not be measurable and you will immediately go into problems, right?
That's right. Actually, we're just assuming finite additivity, but it doesn't really matter for us. We're going to have the finite model property and so on for these logics. But yeah, so we officially, instead of using the power set, we could have, in fact, maybe in the paper we say, I think we do actually, yeah, that mu is just a finitely additive measure on some algebra of subsets of W. That's what
so propositions will be evaluated relative to this algebra that you are talking.
I mean, the problem with that algebra is that you need to be sure that when you take the set of all worlds in which this formula is true, it will still be measurable.
That's right.
To that algebra. Will that be the case?
Yes.
Okay.
And that's basically, the proof is like this, that we require that V evaluates every proposition letter in this algebra.
Into a measurable event, that's okay, right?
Yeah,
but then this will be also measurable, right?
That follows from this point that Lev made about the global nature of the comparisons, right? A comparison formula either evaluates the whole set or the empty set.
Mm-hmm.
So then it remains measurable. But it's an excellent question or point that you make, which is that if you don't do this global thing, but instead for every world you have a set P sub W of measures, then you have to be more careful, right? Because then the truth set of a comparison formula need not be the whole set or the empty set. It could be some non-empty proper subset, and then you need to make sure that that's in the algebra. That's measurable.
Okay.
Yeah. So that's an excellent point. I'm sort of glossing over some of these important details. Yeah.
Can I follow up with a very quick question on this? So am I right to understand that? I mean, you mentioned that, well, yes, you can nest these probabilities, but because the truth of this comparison formula is global, so that basically you can unnest every formula. You can, that is, the nesting is sort of superfluous there.
Yeah, it's like S5.
Yeah. Okay.
Right.
Good. So, yeah.
That's true. So in this talk and in the paper, we're not focused on iteration principles, but you can do that too. Yeah, good point. Okay, so the next step, which is straightforward, is just to translate the axioms of the representation theorem into this formal language. Okay, and you can do that. The balanced condition that every world belongs to exactly the same number of A's as it does B's becomes this really ugly formula, very long antecedent, but it's not hard to write down. And so you then get, thanks to the representation theorem, a complete logic with respect to imprecise probability semantics. And I mentioned before, there's a paper by Burgess where instead of using this finite cancellation condition, he uses this Gabay style rule. So then the axiomatization looks very simple and elegant. You have like that qualitative additivity axiom that I put on the second slide, maybe some other simple axioms like transitivity and so on. And then this nice simple rule. It's a little bit mysterious, this rule. But if you're interested, yeah, look at, there's this paper by Burgess. And we have a recent paper in the Journal of Symbolic Logic called, I think it's called The Logic of Cardinality Comparison. That's probably not right, but something like that, where we explain this rule in great detail. So if you're interested in proof theory and Gabay style rules, I think that's a very interesting case of an application of such a rule. Okay, so now I want to talk about extending the language. So first thing we want to consider is just the vanilla diamond modality. And why do we want to consider that? Well, we want to talk about factual states of affairs and say it might be raining. It's possible that right now it's raining. But we also want to be able to make claims about it might be that hail is more likely than lightning. So we're making a modal claim about a likelihood relation, which is kind of interesting. So this is very familiar in modal logic. This is a little bit less familiar. So how are we going to give semantics for the diamond that allows us to say that it might be that hail is more likely than lightning? Well, the way we do that is by quantifying over the measures in the set. So, a normal diamond, of course, says there is some world where phi is true. Now we say there is some measure that gives non-zero probability to phi. And notice a subtlety here in the superscript. We've changed the set of measures here from p just to the singleton of mu, because we want to say there's some measure in the set such that according to that measure, the probability where you interpret everything in this formula according to that measure, including any comparisons that are in that formula, the probability of that set is non-zero. Okay. So that's the semantics for diamond. And we do two things with the diamond. One is we look at the complexity of the satisfiability problem and actually prove that this logic is still NP complete. And the second thing is axiomatization. And so we have very familiar modal axioms for the diamond, and then some interaction axioms between the diamond and the inequality, which make explicit Lev's point about the global character of our comparisons, that they're either true everywhere or true nowhere. So I'm not going to write all the axioms on the slides for the sake of time, but we do give a complete logic with the diamond as well. Now, most of this diamond business is preparatory for the moves that we want to make with dynamic logics. So I want to spend more time on that. So
sorry,
first, yes.
Sorry, why do you call this epistemic possibility? What is epistemic here?
Well, we're thinking of these measures as sort of subjective probability measures. So it's a sort of, according to an agent, it's possible that it might be raining, or it might be that hail is more likely than lightning, rather than some kind of metaphysical possibility of it could have been that. Had history gone differently, it could have been that. That's not the reading of diamond that we want. We want, for all I know, it might be that. So that's epistemic.
Okay.
Oh, thanks. Okay, so let's talk about dynamics. So we want to talk about learning. So an agent who is represented by a set of probability measures, how do they change their set of probability measures in response to new information? And this is a very standard way of updating that we're going to consider. So if you learn some proposition U with certainty, then what we do is we update the set P of measures as follows. We look at every measure that assigned non-zero probability to U. We keep those measures. We discard all the measures that assign zero probability. So in particular, as we're going to see, at least one measure better assign non-zero probability to U. Otherwise, your set would become the empty set. But we retain all of the measures that assigned non-zero probability to U, and we condition each of those remaining measures on the proposition U. Okay. Where this conditionalized measure is defined as usual using conditional probability. So the probability of V, according to the new one, is just the old conditional probability of V on U. Okay. So because our formal language has comparative probability operators, we can now model updating with what we would call a mixed ontic epistemic formula. So it can say something purely about the world, like it's raining, but it can also say something like it's more likely that there will be hail than that there will be lightning. And you can update with such a mixed formula. I can learn this. You could tell me, it's raining right now, and it's more likely that there will be hail tonight than that there will be lightning. And I can update my set of measures by that. Okay, I'm going to discard all the measures that gave this zero probability, and then I'm going to condition all the remaining measures on what I've learned. And actually, because of the discarding, when I discard all the measures that gave this zero probability, I'm going to be left with measures all of which agree that H is more likely than L. So that's how I'm going to learn new comparative probability facts from you. So now we follow the style of dynamic epistemic logic in adding dynamic operators to the language. So this means after update with phi, psi is the case. So this is true if and only if, well, first, there better be some measure in your set that assigns phi non-zero probability. Otherwise, we would have the collapse into the empty set. So supposing there is at least one, then what we do is we just ask whether psi is true after updating the set P by phi. Okay, and here again, I've just written it out. What is P updated by phi? You look at all of the measures in your initial set that assign non-zero measure to the truth set of phi. You keep only those, and you condition each of them on the truth set of phi according to that measure. But each measure has its own view of the world. That's why we have this singleton V up in the superscript. And we update mu by conditioning on mu's view of the truth set of phi. Okay. All right, so this is what I said before. This dynamic operator, to evaluate it, what do we do to the model? We discard all measures. This is in effect what happens. We discard all measures that don't satisfy that H is more likely than L, and we condition each of the remaining measures on the factual thing R. All right, so now I want to put up some axioms of this logic, and this is in the style of dynamic epistemic logic where we have reduction axioms that actually allow us to rewrite formulas in the dynamic language as equivalent formulas without the dynamic operator. So this is that kind of template that you see instantiated again and again in dynamic epistemic logic. So this logic is the smallest set of formulas in this language that first of all is closed under modus ponens and the rule of replacement of equivalence. So if two formulas you can prove the biconditional between them, then in any formula, you can replace P by either of them. Mm-hmm. It contains all theorems of the static logic of imprecise probability. and then the following reduction or recursion axioms. Okay. The most interesting of which, so these first three, four, the first four are kind of very familiar looking from dynamic epistemic logic. And the interesting part are R4 and R5, right? So now you can see why we introduced this diamond ahead of time, because we were thinking that we would need it when it came to axiomatizing the dynamic logic. So R4 says that after you learn phi, when is it the case that you now judge that alpha is at least as likely as beta? Well, first of all, there's a precondition of this update with phi that there at least be some measure that assigns phi non-zero probability. You have to at least consider it possible that phi is true in order to update with it. And then what it should be is that for all measures in your set, remember the box now quantifies over all measures. For all measures in your set, basically it's saying that conditional on phi, that's what this conjunction is doing. It's saying conditional on phi, alpha is at least as likely as beta. And of course, that's what we always want in probability, that you can read off from the initial probability measure, looking at the conditional probabilities, you can read off what your new probability judgment should be after learning. Well, this is very much just the standard Bayesian idea that you can read off the new credences after learning from your old credences conditional on the evidence. And something similar happens with the strict relation, although we have to remember that we throw away all measures we throw away all measures that assign zero probability to phi. So that's why we have this conditional that says in the original model, it just needs to be that all of the measures that assign non-zero probability to phi are such that the probability of alpha conditional on beta is on phi is at least as greater than the probability of beta conditional on phi. Any measures that gave phi zero probability, they're going to be thrown out. So we don't need to check that those measures, the ones that are thrown out, will satisfy this condition that the probability of alpha conditional on phi is greater than the probability of beta conditional on phi. Okay. So these are not, this is not rocket science. These are kind of what you would want to expect in terms of Bayesian conditionalization. And we proved that this is sound and complete by this reduction axiom strategy, where we just proved that every formula in the dynamic language can be translated to an equivalent one in this language. And then we take advantage of completeness in this language, which, remember, in turn relied on the representation theorem. So it's a lot of building on what you've done for the earlier systems. Now, there is an exponential blowup in the size of formulas when we apply these axioms to translate the dynamic formulas to the static formulas. And so an interesting question here is there a satisfiability preserving translation with only polynomial blowup? So Karsten Lutz showed in the case of public announcement logic, which is like the simplest dynamic epistemic logic that people consider, although the standard reduction axioms for this logic also lead to an exponential blowup in formula length, he comes up with a clever translation, which is, it's only satisfiability preserving, but that's all you need for this kind of result. And it's an interesting question whether the same is true in this probabilistic context. Okay, I'm at my last little part. I'm sorry that I overshot a little bit what I was expecting. But this is, in a way, I think maybe one of the more interesting parts, actually, of the talk, becoming aware of a proposition. So there's a big literature in economics about awareness and unawareness. So this is very much related to that. And we want to model examples like the following, which was inspired by an example of Johann von Bentho. A patient learns from her doctor of the existence of a gland in the human body and of a disease previously unknown to her. So she'd never heard of these things before. And then the doctor tells her that if her gland is swollen, then it's more likely than not that she has the disease. Okay. Then subsequently, her gland is examined and she learns that it is swollen. So she puts 2 and 2 together and makes the logical inference now, okay, it's more likely than not that I have the disease. So very simple example, but we want to be able to model this in our dynamic setting. So first question, how should we model the patient's becoming aware of the existence of this gland, or the proposition, you know, that your gland is swollen? Never contemplated that proposition before. Also never contemplated the proposition that I have this disease that I've never heard of. Okay. So standard Bayesian probability, you know, kind of imagines that you start out with this rich state space and algebra propositions, and doesn't really ask what happens when you learn about some whole new concept. How should the state space and the algebra propositions change? So first, let me introduce the formal language. So what we're doing is we're adding these new operators indexed by propositional variables. So we have IP plus and IP minus, and the intuitive reading of these, IP plus is, suppose we introduce P as a true proposition that the agent now just became aware of. After we do that, then phi is true. So it's another dynamic operator. After we introduce the agent to this new proposition, which happens to be true, phi is the case. Or we can say, after introducing the agent to this proposition P, which happens to be false, then phi is the case. And we can also, as an abbreviation, just write I, meaning that after we introduce a new proposition P, whether it be true or false doesn't matter. In either case, phi is going to hold after we introduce the new proposition. Okay.
And phi may depend on P or not?
Yes, yes, phi can contain P. That'll be actually very important. Yeah, good question. Okay, so how do we model this semantically? Well, this is kind of an obvious idea, right? You just take each world and you split it in half. So you split it into a world W, 0, where P is false, and then into a world W, 1, where P is true. So what we're doing is we're moving to W cross the set 0, 1. And this has a standard analog for Boolean algebras, where you add a new element to a Boolean algebra. But I'm just going to explain it here in terms of the dual side, in terms of sets. Okay, so we move to W cross 0, 1. And now what I need to explain is, how does our set of probability measures on our original W turn into a set of probability measures on this split world set? So let's say we have a field of sets F on W and evaluation V such that V of Q is in the field. This is the thing I was talking about earlier for all the proposition letters. Okay, so first thing is V plus of P. What it's saying is, for every proposition Q that's not P, we basically just copy it to the new, richer set of worlds. And Q doesn't really distinguish, between 0 and 1. P is the proposition, which is true in all the worlds whose second coordinate is 1, and false in all the worlds whose second coordinate is 0. That's the key point. But it's only P that cares about this splitting. Everything else is just sort of copied over to this bigger space. So that's V plus P. And then given a model, a propositional model, we'll let M plus P be this richer set of worlds together with this special valuation that makes P true on all the worlds, exactly the worlds whose second coordinate is 1. Okay, now for the probability measure part. So first thing we can do is just sort of copy the old field of sets F to a corresponding field over this product. So we do that in the obvious way, just look at every proposition in the old field and then take its product with this set 0, 1. So there we're just copying the propositions over. Then we want to say that split F is the smallest field of sets that extends F together with the proposition saying that P is false. Because we do want a new proposition. So we don't want to just copy up, we don't want to only copy over all of the old propositions. We want to create a new proposition, namely like P is false. Right? We want to have the P is false proposition, and we also want to have the P is true proposition. And that's what this is doing. So we're actually getting a new proposition. Well, not just one, get its negation and so on. Now, for any finitely additive measure, mu, on the old field, we can copy it over as well onto this new field, F cross 2. So we can have mu cross 2, and that simply says that the measure of the copy of proposition X in this new field is just the old measure that mu gave to it. Again, just more copying over. Okay. Okay, that's just notation. So we'll let P cross 2 be the family of all these mu cross 2s. And now here's the key point. What is our new set of measures? Split P, it's the set of all finitely additive measures, mu, on our new field, such that when you restrict mu to just the old propositions, it agrees with the copy of some old measure. So what this is going to do is it's going to leave your attitudes toward all of the old propositions, Q, R, and S, that are not P, the same. But then for P, you are maximally ignorant about this newly introduced proposition P. So you have all possible probability values for P. And that's the idea. You know nothing about this new proposition. Somebody needs to tell you something about the new proposition before you can make any judgments about it. When you initially introduce it, you have like full uncertainty about P. So for every possible probability value that you could assign to P, there is some measure in your set that assigns that measure to P. Okay. So sorry about all the notation in this slide. But once we have it, now we can state the semantics for these new dynamic operators. So after the introduction of a new proposition, which happens to be false, that's what the minus means, phi is true at W relative to P, relative to M, just in case when we introduce the new proposition P and split all the probability measures in the way just described, then phi is true at the copy of W where we made P false. Okay. And the analogous condition for a true proposition. Okay. So we split every world in half, make you maximally ignorant about the probability of phi, probability of P, excuse me, and then we ask whether phi is true. Oops. Now how can we use this? And this gets back to Lev's question about does P occur in phi and so on. Well, this sentence that I've written here, this is actually a valid formula, and it represents this medical example. When we take the proposition introduced by IP to be that the agent has the disease, and we take the proposition introduced by IQ to be that the gland is swollen. So here's how we're thinking about this formula. It says, after the doctor introduces this new proposition P, that the agent has the disease, now she can contemplate that proposition. And initially, we assume that she's not feeling bad or anything. So initially, she thinks it's more likely than not that she doesn't have the disease. That just makes this example more interesting. So the doctor tells her about this disease. She does an observation of herself. She thinks, oh, it's more likely than not that I don't have the disease. Then the doctor introduces this new proposition that your gland is swollen. Now she can think about that proposition. And here's the key part. The doctor gives her some comparative probability information, namely conditional on the gland being swollen. So we have the Q here in both conjunctions. Conditional on the gland being swollen, it's more likely that you have the disease than that you don't. So what's that going to do to the set of measures? Well, it's only going to retain the set of measures that agree with that comparative probability judgment. Then finally, she updates on a purely factual proposition that her gland is swollen because she had some diagnostic test. She does Bayesian conditioning on all of the measures in her set. And then indeed, the final result is that she concludes that it's more likely than not that she has the disease. So here in a single formula, we basically build up the state space. You could have started from a single world where the agent sort of thinks about no distinctions. And then through these dynamic operators, you actually build up the state space and then modify your measures with new comparative probability information. I'm getting to the end here. What's interesting about this language, actually, is that it allows us to express comparisons of linear combinations of probabilities with rational coefficients, which is initially surprising. But here's the basic idea of how you do this now. We can say that one proposition is more than 3/4 the probability of another, and so on. The way we do this is by introducing new propositions that stand for independent coin flips coming up heads. And we use the update with comparative probability formulas to tell you that these coin flips are independent. So for example, if we look at this formula, this says that the probability of P is greater than 3/4. So what it says is, think of Q as the proposition that the coin in my right hand comes up heads, and let R be the proposition that the coin in my left hand comes up heads. I'm sorry I haven't introduced this, but of course this just means that, that's at least as likely as that, and that's at least as likely as that. So they're equally likely. So it says Q and R is equally likely as Q and not R, and Q and R is equally likely as not Q and R, and Q and R is equally likely as not Q and not R. So that's setting up the fact that these are these independent coin flips, right? So then the probability of Q and R should be a 1/4, and the probability of not Q and R should be 3/4, and then we say that P is greater than the probability that they'll both come up tails. Greater than the probability that they will not both come up heads. That's different. Okay. So actually, basically following this simple idea, we can prove that if you have any sequence of formulas, phi i's and psi i's, and any sequence of natural numbers, ai's and bi's, then you can write a formula chi in the language with our I operators, such that chi expresses that for every measure in your set P, the sum of the measures of the phi's with these weights, AI's, is greater than or equal to the sum of the measures of the psi's together with these weights BI's. So this is what we're talking about, these linear combinations with natural number coefficients, but then by dividing, you can think about rational coefficients. Mm-hmm. So this is actually a very expressive language. And this leads to the open problems that I want to conclude with. So first, although we have sound and complete logics for all of the previous systems, we stopped right there at I. So it would be very interesting to find an axiomatization of the set of valid formulas in the language with I. And this is very much related to previous work in computer science on logics, very expressive logics for probability comparisons, linear combinations with rational coefficients. What's the complexity of the satisfiability problem for the logic with I? We also don't know that. If people are interested in dynamic logics and probability and logic, I encourage you to think about these problems. And then finally, the problem I mentioned before, which is just the complexity of the satisfiability problem for the language of like Bayesian update in imprecise probability. So those, if there are any students in the audience or anyone else interested, I'd love to talk to you about these problems. But let me now just say a few things in conclusion. So I think comparative probability, it's an old topic. It's, relatively, going back to the 50s and so on. I guess not in the grand sweep of logic. It's a very new maybe topic, but I think it still remains a rich area for logicians. I think even we could have this influence our pedagogy. So when we're teaching introduction to logic, we could introduce relative likelihood right after the Boolean connectives. And I think this might be useful for students to start thinking about how to reason systematically about comparative probability. On a more research side, we could take Boolean algebras equipped with this binary relation as objects for study in the sense of algebra, develop representation theory, duality theory, and so on. And in general, I think this is just part of a greater hope to see fruitful new contacts between logic and probability as we advance in the 21st century here. So thank you very much for your attention.
Okay, thank you very much. That was very interesting. Okay, yes. Okay, I presume there will be many questions. So Stanislav, please begin with your.
Well, I have a number of questions. Well, the first question concerns the representation theorems you mentioned. So there you have just an arbitrary set of measures, right? Will
Yes.
anything change if you assume that this set is convex closed or something like that? Some standard condition on that this set is closed under thin combinations or?
Yes. I think actually, if you look at the proof, you know, we can say more about the set of measures than just that it's agrees with the relation. But in general, there's a whole literature on asking for additional conditions. So I think if you look at our paper, it's called a note on cancellation conditions for qualitative probability or something like that. We discuss some of the other conditions that people ask for, and then the corresponding axioms for the comparative relation. So, you know, sometimes when you ask for some property of the set of measures, you then have to augment your set of axioms. And there's some work by Alon and Lehrer, economists. It's interesting that a lot of this comes up in the economics literature, and they definitely want additional conditions on the set of measures, and they identify the additional axioms that you need on the comparative relation. Let me make sure the reference here. Let me go back to my slide, and then I'll write the reference. So basically, they take this theorem, but that's hopefully I spelled that correctly. If not, I apologize. And this is cited in a number of our papers. I think it's in Journal of Economic Theory. And what they do is they basically prove analogs of this, but in the infinite case, and they ask for additional properties of the set P of probability measures, and then identify the additional qualitative axioms. So I think this is the go-to place to learn more about additional conditions.
Okay, I have one more question and one comment. Well, the second question, it concerns the completeness result, even for the first logic you mentioned. Now, for the very last language, you already have, I mean, on the quantitative side, if you assume all the measures to be countably additive, then the compactness fails immediately, right? And it's easy to do that. So the question is whether any of your languages will satisfy the compactness theorem, provided that all measures are assumed to be countably additive. It is certainly not true for the last language because you can express linear inequalities, but will that be the case for the first two, for instance?
Yes, good. Well, since we have, these logics are going to be sound, and we have completeness via FMP. I mean, we have the finite model property. And of course, in that case, all the finitely additive measures are trivially countably additive. But I guess, yeah, the thing that we've been focused so much on is just a finite set of worlds and finitely additive measures on the power set. So it's a great question about countable additivity, but I don't even think we really address it at all. I
mean, because if you have an infinite set of premises, then
exactly.
this question will arise naturally.
Yeah,
if you can
exactly.
say mentioned that like the probability of a given proposition is less than 1/2, 1/4, then it has to be 0, but it cannot be, I mean, expressed in a finite form.
That's a great point. Yeah, I think the closest we've come to addressing these issues about strong completeness and compactness is in the JSL paper, which is related. It's on comparative cardinality. So we're comparing the cardinality of sets, which may be infinite. And there we talk about failures of compactness and strong completeness in the final section of that. And that's very interesting, actually. Like you said, using infinite sets of premises to express things. So that's the closest to anything that we've written about the compactness and strong completeness of these logics. So.
Okay, and just one small comment concerning the first open problem you mentioned, right? Yes. Can you go to that slide?
Sure. Oh, sorry. Go back. Yeah.
Yeah, I think that in general, I mean, I think it should be possible, and roughly the reason is because, I mean, the quantitative language for reasoning about linear inequalities can be easily axiomatized, right? And this is well known. You have a lot of problems when passing to polynomial equations, then you have no axiomatization for the quantitative language, or at least no one knows what is a nice axiomatization for that. Yeah. But for linear inequalities, it should be the case. So maybe even from the old paper by Fagan, Halpern, and Megiddo, you can try to extract that. Well, maybe, I mean, I have no idea what you can.
Exactly.
But it seems feasible, right?
Absolutely. That's exactly the paper I had in mind when making connections with the computer science literature. Yeah, so I should have said find a nice axiomatization. So, you know, we don't want to just say, oh, it's decidable, you know. So we have
Sure. You want to have a nice axiomatization because for the polynomial case, you have, well, everything is decidable, but no one knows how to provide a nice axiomatization. But for linear inequalities, you know that. So, I mean, maybe that's a way to go. Okay, thank you.
I hope there is a nice axiomatization.
Valentin, you have a question.
Yes, thank you. But maybe I should go last since I'm kind of external visitor to this seminar. So if there are other people who want to ask questions.
No. You raise your hand, you go.
Okay, good. All right. Well, yeah, first, thanks, Wes, for the very interesting talk. I have a couple of sort of light half comments, half questions. So the first one concerns this Ellsberg's paradox, which I had only vaguely seen before that. And when you presented it, then I expected some slightly different version, which is even more paradoxical. So I want to ask you on that. So imagine this. I mean, the argument that you presented for the betting red against what were the colors like blue and yellow, so against blue, right? So so the same argument applies for betting red against yellow. So that those people who would prefer to bet, let's say, $1 on red against $1 on blue, they would also prefer to bet $1 on red against $1 on yellow. But they would certainly not prefer to bet $2 on red against $1 on blue or yellow. So that clearly some additivity is failing here in a very sort of obvious way. And I wonder what are the consequences for, so that is for those who actually find this preferable, this first bet preferable, something goes horribly wrong. What is it, and what's the message?
That's a great question. Yeah, I mean, economists have considered non-additive measures to model people's behavior under ambiguity. So I think Gilboa and Schmiedler are the names there that have looked at non-additive measures. I mean, they satisfy some properties, which is not full additivity, right? It's not like anything goes. They have monotonicity and maybe sub or super additivity or something.
Maybe they are just should be considered to be non-rational, and you know, modeling non-rationality. Maybe it's an issue, but you know,
it's one of those Kahneman-Tversky sort of phenomena that people slip down the non-rationality slope without noticing this, because, well, I mean, whatever measure you introduce, even if it's not additive, then still common sense says that no one would actually do the last bet, that is 2 on red against 1 on blue or yellow. That is against sort of common sense probability, right? But well, okay, so
so in the set of measures representation that I gave, I mean, all the measures agree that the probability of blue or yellow is 0.7.
right. Okay.
So I think it avoids your problem, right?
No, it actually creates it, because
maybe I
mean,
didn't
again,
understand your example.
if you would prefer to bet $1 red against $1 on blue, then you're already in trouble, because by token you have to. Right. So that was my point. But anyway, so yeah, I want to read more on this, and I'll leave it for later. But can I make one more comment and perhaps a question? So I see some parallels, some sort of intuitive parallels with what you are doing here with what people do in value theory, of which I don't know much. I know actually very little, but I've heard some talks, and there was a student in practical philosophy who is consulting me on things. So I mean, value theory basically compares values of things in terms of goodness and badness, and so on. And some things are incomparable on one hand. On the other hand, though, they argue that there are some things that are incomparably worse than others. Like, for instance, dying or being burnt alive is incomparably worse than any number of mild headaches, right? So that it seems, on one hand, it seems technically sort of close to comparing this sort of, well, how do you call them, subjective probabilities. On the other hand, there seem to be some technical differences, so that I wonder how far this parallel goes, if you have ever given a thought on this, and how much of your results can actually faithfully transfer there. That's my question. And I also want to add this, that I think I see a natural interpretation of this generalized, what was this, finite cancellation, in terms of this incomparably worse or better values. If you see what I mean, I can explain this a bit more. But before that, you tell me, how far does this parallel go with value theory?
That's a great question. So I would say that that's about non-Archimedean utility theory. So the idea that, you know, somebody being tortured is worse, like, than n people having headaches for any n.
Right.
Non-Archimedean utility theory. And
so would you consider non-Archimedean probabilities here?
Yeah, that's also something. In fact, right now I'm co-teaching a probability seminar at Berkeley with Paolo Mancosu, one of my colleagues, and yeah, we're considering things like non-Archimedean probability. That does not play any role in this paper, but I do think it's interesting, and I don't know that people have looked into it enough, of using comparative probability, thinking about comparative probability in the context of non-Archimedean probability, hyper-real probability, you know, probability and non-standard analysis. There's been a lot of work recently on not using the real numbers, but using other things like the hyperreals and Robinson non-standard analysis and stuff. And you could connect that with comparative probability too. And you know, that has come up because people want to think about thought experiments over infinite state spaces where everything is equally likely, and they want to think about infinitesimals in those contexts. But I don't think there's so when you said like incomparably worse, I kind of correct me if I'm wrong, but I kind of think it's an equivocation on the ordinary meaning of incomparable, because those things they're not actually incomparable. It just is worse. It's just so much worse.
Yeah, right. Yeah, I see. So, and clearly that's not a good term, but it somehow has stuck in my brain. Maybe it's just my imagination. But people do use this sometimes in you know, everyday speech. So anyway, as I understand, the parallel goes somewhere, but it doesn't go too far, and probably not much of, or how much of what you have done here can actually be transferred to results in value theory. That makes
Well, you know, Val, it's kind of in the same world in the sense that deviations from classical expected utility decision theory. So, you know, if you think about this imprecise probability approach together with this decision rule that I mentioned down here, this deviates, if you think about the axioms on preference that go along with this, it deviates from the classical von Neumann-Morgenstern axiomatization of expected utility theory. And so does your non-Archimedean utility theory. So in the sense, they're both in the vein of like alternatives to classical expected utility.
Okay, thanks. I can ask more, but I'll stop for now.
Okay, Alexander Gerasimov has a question.
Okay. Does it make sense to compare your probabilistic approach to reasoning about uncertainty with another such approach, namely mathematical physiologics?
Yes, I think it does. I don't have much to say about it, but I definitely remember when I first got to Berkeley, I had some conversations with Latvizada about fuzzy logic. Actually, Dana Scott, Latvizada, and I sat down and had several lunch meetings where we tried to have a meeting of the minds and try to understand how these things are related. I don't have a considered view on what the relation is between the stuff in this paper and fuzzy logic. Let me just mention one thing, which is possibility measures. So there is stuff on comparative probability and possibility measures, where a possibility measure says that the measure of A union B is the max of the measures of A and B, instead of the additivity condition. So there is work on that, I think by Halpern and others. So that makes perfect sense to think about possibility theory instead of probability theory, and then look at the corresponding comparative probability, I guess we would call it, I don't want to say, comparative possibility logic. I think that's a nice idea.
Okay, thank you.
Thanks.
Okay. So, okay, then I also would like to ask a couple more very general questions. So one question is purely sociological. So obviously there is a huge literature on this topic, on some related topics. So where are the most, let's say, where the people doing that sort of study are concentrating, in economics or where? So what are these, the researchers on this?
Yes, I think in the imprecise probability, it's fairly interdisciplinary, and they have their own meetings and conferences and so on. So I think people coming from economics, statistics, maybe some from computer science, and then philosophy. There's been a lot of discussion in the last couple decades about imprecise probability representations. Also go under the name of mushy credences. There might be some other buzzwords associated with them. So I think it's a pretty interdisciplinary affair, and I don't know exactly if it's more heavily weighted in one area or another. I haven't attended these imprecise probability conferences, but there was one maybe last year or the year before, and you could kind of get a sense by looking over the program of how interdisciplinary it is. As for the comparative probability, that's mostly has been logicians and people interested in foundations of probability. So people like Dana and Pat Suppies, and in the early days. Well, first of all, there's the famous book, Foundations of Measurement, by Krantz et al. Krantz, Luce, Suppies. So, they just consider a very general question, which is if you have some qualitative structure that represents your measurements, like you're weighing objects and you have a balance or something. when can you then obtain numerical assignments of masses or something like that? So measurement theory is very much related to it. You could say that this is a special case of measurement theory. We're just measuring, you know, subjective probability or something like that instead of measuring mass. So that's another place on the comparative probability side where you see a lot of literature is in connection with measurement theory. Measurement theory, not in the quantum mechanical sense, but in the sense of going from qualitative to numerical representation.
Yeah. Okay. My second question was also somewhat on the general side. So about this comparative. So here you have, you started with this comparison probability or comparative probability. What is the right term? Comparative probability, right? So this less than relation, comparative, yes. So, and then, okay, you come to this representation theorems where you want to impose the conditions which would ensure that, okay, you deal, in fact, you can, okay, this comparison corresponds to the relation coming from a family of probability methods, or even a single probability method. But why do we actually want to do that? So why do we want to recover the numbers from this relational structure? So maybe it's good taste to deal with this purely qualitative kind of reasoning. So why do we need it?
That's an excellent question. So I think one reason is you just want to know what would it take for your qualitative relation to conform to some probability measure. So
mathematically, that's a perfect question. Yeah. The first question one would ask. So
first question. Exactly. So more philosophically, you could think that the real thing is qualitative judgments. So this also happens in decision theory, where in a sense you might think the real thing are people's preferences between different actions. And that's qualitative. Like, you know, I prefer this to that, or given a choice between these two things, I would definitely choose this thing. There's no numerical aspect of the binary choice between two actions or something like that. But the person can be represented as if, right, they have a utility function of a probability function and they're an expected utility maximizer. But we needn't think that there's any, you know, psychological reality to that, right? It's just they can be modeled as if they were doing that. But you might think that the basic thing at the level of reasoning is not, does not involve numerical representations. Of course, I don't have a view as a matter of cognitive science about whether people in fact reason in a more qualitative way or anything like that. I do think that when it comes to inferences in natural language, you know, ordinary language does contain these expressions like this is more likely than that. And so, you know, logicians like studying inferences that look valid. And I think that from that point of view, it makes sense to just take this greater than or equal to as a primitive thing and think about what the valid patterns are. And, you know, you might at the end of the day, I think, accept a logic for this greater than or equal to that's not exactly the logic of, you know, precise probability or imprecise probability or something like that. So, you know, there may be a kind of pre-theoretical notion of at least as likely as reasoning that then through the development of science, we kind of morphed into, you know, Kolmogorow's probability and everything. But maybe you can also just ask about the logic of ordinary thinking about more likely than. And maybe it doesn't have to have these finite cancellation conditions. So one of the things we did in one of the early papers on this is we just raised the question of what kind of data about speakers of natural language would be able to discriminate between the hypothesis that the semantics of the language validates what we call the Di Finetti logic, which is a kind of weaker and simpler logic. says that this relation is reflexive and transitive and it's qualitatively additive, say. That's one hypothesis, that the semantics of at least as likely as in natural language, it just determines that much, that this relation is a diff and eddy relation. Another hypothesis is the semantics of the more likely than, or at least as likely than in English, say, it actually determines the full probability logic, right? And we wondered what data could distinguish between these two semantical hypotheses for a natural language. And we raised some doubts about whether you could distinguish them. So maybe a semantics that gives you this diff and eddy logic is viable. You don't have to go all the way to mathematical probability in order to give semantics for at least as likely as in natural language. But anyway, that's an interesting question to contemplate. So I think that the diff and eddy logic, I think, is interesting. And we could consider alternative semantics for the diff and eddy logic, beyond just the obvious algebraic semantics, which just says, oh, well, interpret the less than or equal to as a relation in a diff and eddy algebra. So here's another open question that I will pose here. Can we have an interesting representation theory for these diff and eddy algebras, diff and eddy relations? And by that, I mean,
yes.
You have a binary relation that's reflexive, transitive, and so on, and satisfies this qualitative axiom.
Yeah, if the answer is that if you impose sufficiently many axioms, you can, up to some equivalence, uniquely extract the probability measure or a family of probability measures up to some kind of isomorphism or something like that. So really representation.
Yes.
That would be some kind of satisfactory answer to this, because we say, okay, qualitatively we believe in these principles, and then we can equally well deal with the measures. It's mathematically more convenient, and then we are done. But there are no such uniqueness kind of results here. So suppose we have these conditions like cancellation properties. What can we say about the different measures that deliver the same relation?
Yes. Yeah. So I mean, you can ask for additional conditions and ask about uniqueness, which people do also in the infinite case. Of course, in the set of probability measure case, you can just look at the set of all measures, like look at the biggest, the biggest one that add every measure you can, which doesn't break the agreement between your qualitative relation and your set of measures. So actually, in another paper, we consider, for example, if you have an ordering on a set, not on the power set, but just on the set. So an ordering on worlds, right? Then what you can do is you can look at the set of all probability measures that almost agree with the ordering on worlds, where almost agree means that if the ordering on worlds says that world W is more likely than world V, then the measure says that the measure of the singleton of W is at least as great as the measure of the singleton of V. So almost agreement is just one direction instead of the biconditional, whereas I was talking about a biconditional. But almost agreement just goes from the qualitative side to the measure side. And you can consider the family of all measures that almost agree with the qualitative relation. And then you can ask, well, what is the unanimity qualitative relation on propositions that you get from the set of all measures that almost agree with the qualitative ordering? So that's to make the set of measures as big as you can. Throw in as many measures as you can. So that's another way in which you can try to relate the qualitative to the quantitative. But what I had in mind with diff and eddy was actually not necessarily any kind of probability measure or measure-like representation. I mean, any kind of more concrete representation than the purely algebraic one. I think would be really interesting. If we could get some duals to diff and eddy algebras that give us some insight I don't care what they are. I don't require that they're related in some way to probability measures or anything. Just any kind of duals, I think, would be very interesting to have.
Okay. Okay. Thank you very much. That was a very interesting talk.
Thank you.
Okay.
Thanks everybody for the great questions. And thanks again for the invitation.
Okay. Yes. We will repeat it after some time when you have a new paper. Okay. Thank you very much.
All right, take care.
Okay. Then goodbye, everybody.
Bye.